everyone. In this video, we'll talk a little bit about conditional probability. So what happens when we need to restrict or limit our sample space? So we'll start by defining conditional probability. We'll then work up to a pretty important theorem called Bayes' theorem and see how we can use that to flip the conditions. So let's start with the definition of conditional probability. Conditional probability is the probability that an event occurs given that some other event has already occurred. So we say this as the probability of A given B. In probability notation, we write this as the probability of A with a vertical bar, then B. So what comes after that vertical bar is what's given. That's the condition that has been met. In order to find conditional probability, what we do is take our sample space and restrict it. So let's say that we already know, or we're conditioning on the fact that we fall within this green circle for B. Given that we know we're in B, how can we find the probability that we're also in A? Well, let's just take the area where the two circles overlap, so A intersect B, or A and B, divided by the probability of B. And that's how we get or define conditional probability. So diabetes and chronic kidney disease are two diseases that are increasing burdens on the senior population in the United States. We have data from a large national sample of visits to the VHA that indicates that vets in their 60s, about 8.3% of them have stage 3 through 5 CKD, chronic kidney disease. This rate is 14.1% among vets with diabetes and only 6.4% among vets without diabetes. So before we do any kind of calculations with this data, let's just work on getting that probability notation. So we're going to let C be the event that a vet in their 60s has stage 3 through 5 CKD, chronic kidney disease. We'll let D be the event that a vet in their 60s has diabetes. So the statement here, 8.3% of vets in their 60s have stage 3 through 5 CKD. There's no condition on that. Our population that we care about is vets in their 60s. We're not conditioning on some other event having taken place. So the probability of C is 0.083. The next statement, this rate is 14.1% among vets with diabetes. Now that is a conditional statement. We are conditioning or limiting ourselves here only to those vets with diabetes. So here we're referring to the probability of C given D. The next statement, only 6.4% among vets without diabetes. Now we are again conditioning, but we're conditioning on something a little different. We're now limiting ourselves to only those vets who have diabetes. So we can find conditional probabilities through applying a result called Bayes' theorem. And Bayes' theorem states the following. For any two events A and B, the conditional probability can be written in the following way. The probability of A given B is the probability of A and B divided by the probability of B. So take this Venn diagram, for example. If we'd like to find the probability of A given B, here's what we'll need to do. We'll first find the probability of both A and B, that's 0.3. To find the probability of B, we'll take 0.3 plus 0.2, so 0.5. So our solution here, our probability of A given B is 0.3 divided by 0.5, or 60%, 0.6. The major idea here is to think of conditioning as restricting our sample space. We're no longer interested in everything that could happen. We're just interested in what could happen if B has already happened. So VHA records suggest that 25% of vets in their 60s have diabetes. So here's what we'd like to do. We'd like to find the probability that a randomly selected vet in their 60s has both diabetes and stage 3 through 5 CKD. Here's how we could do that. Here's what we know. We know that the probability of C is 8.3%, 0.083. We know the probability of C given D. We know the probability of C given D complement, or not D. and we also know the probability of D itself. What we want to find is this. We want to find the probability of C and D both occurring. We can do this by just rearranging the conditional probability definition. So here's our definition from Bayes' rule. The probability of C given D should be the probability of C and D divided by the probability of D. Rearranging that, we get that the probability of C and D is the probability of C given D times probability of D. We now have two things. We know both of them. So the probability of C and D turns out to be 3.5%. Let's take a look at another example. So according to the American Society of Microbiology, the probability that a man washes his hands after using the restroom at an airport is 74%, and the probability that a female washes her hands after using the restroom at an airport is 83%. This data was gathered or was collected from an observational study at an airport. So yes, there were people watching in the bathroom. Kind of weird. Oh, suppose that a waiting room in an airport contains 40 men and 60 women. We will also further assume that all passengers in waiting are equally likely to use the restroom. What is the probability then that the next individual who goes to the restroom will wash their hands? So here's what we know. We know the probability that the next person will wash their hands given that they're a female is 83%. Probability that the next person will wash their hands given that they're male is 74%. We're also assuming that this waiting room is made up of 60 women, 40 men, so 60%, 40% probabilities. We want to find this. We want to find the probability that the next person, ignoring gender, washes their hands. So here's what we're going to do. I'm going to take that probability of H and I'm going to split it up into two smaller groups. I'm going to claim that the probability that a person washes their hands is the same as the probability that the person washes their hands and they're female, plus the probability that they wash their hands and they're male. So I'm just going to take that hand washing and break it up into the two parts. I'll then apply that rearrangement of Bayes' rule that we used in the previous example. So the probability of H is equal to the probability of H given F times the probability of F plus the probability of H given M times the probability of M. Now we have everything in terms of probabilities that we know. So we'll just plug in the given values and get a probability of 0.794. So there's a 79.4% chance that the next person who goes to the restroom will wash their hands. Now let's extend Bayes' rule just a little bit. So let's let A1 through AN be disjoint or non-overlapping events that cover the entire sample space. Then that trick that we just used with the hand wash isn't a unique trick. We can use that anytime we have disjoint events over the entire sample space. So we can write the probability of, say, event B as the sum of the probability of those disjoint AIs and the B. We can then extend Bayes' rule, so just taking this new definition of the probability of B, sticking it in the denominator, and then we can use this in a pretty clever way, and we'll show you with this example. So rapid HIV tests allow for quick diagnosis without expensive lab equipment, so they're pretty popular for that reason. However, their efficacy or how well they work has been called into question. We have data from a population of 1,517 tested individuals in Uganda, of which 4 had HIV but tested negative, 166 had HIV and tested positive, 129 did not have HIV but tested positive, 1,218 did not have HIV and tested negative. So here's what we'd like to find. We'd like to know the probability of a false positive. We'd like to know the probability of a false negative. We would also like to know if somebody tests positive, what's the probability that he or she actually has HIV. So let's jump into the false positives first. Now, this false positive terminology in the health sciences can be a little misleading because it's used in different ways. Some people will refer to false positives as being an unconditional probability. Others will refer to it in a conditional way, and we'll see what we mean. So what's the probability of a false positive out of the overall tests? So unconditionally. Well, there were 129 false positives, people who did not have HIV but tested positive, out of 1,517 total, so about 8.5% of the overall tests are false positives. Now, what if we want to condition? What if we want to say, well, out of the positives only, how many of those were false? That's going to be a slightly different probability because we're now only looking at the positives. So the probability of H complement not having HIV but testing positive is much higher, about 44%. Same idea with the false negative rate here. That false negative rate overall is going to be much less than the false negative rate conditional on a true negative. So let's say that we have a randomly selected individual who tests positive on a rapid test. What's the probability that he or she actually has HIV? That's likely the probability that you want to know if you're being tested. So we want to find the probability of H given P, a positive test. We'll start with the Bayes rule definition. So that is the probability of H and P divided by the probability of P. We can get those just by using the numbers in the table. So we get 166 out of 1517 for the HIV positive and testing positive. The overall probability that someone tests positive, there were two groups where that occurred. So even for someone who tests positive using this rapid test, there's still only about a 56% chance that they actually, in fact, have HIV. Let's take a look at one more example. So cystic fibrosis is a hereditary lung disorder that is often fatal. CF can be inherited only if both parents are carriers of an abnormal gene. This gene was identified in 1989. It turns out that the probability that a randomly chosen person carries the abnormal CF gene is 0.03. The CF20M test detects most, but not all, harmful mutations of this gene, so it can be wrong. The test is positive for 90% of people who are carriers. The test is positive for 1% of people who are not carriers. So if you test positive, what's the probability that you are actually a carrier of the gene? So I'm going to let P be the event that the test is positive, C be the event that the individual is a carrier. We know that the probability of C is 0.03. The probability of a positive test given C is 0.9. The probability of a positive test given not C is 0.01. We want to find probability that you are a carrier given that you are positive. Again, we'll start with the Bayes rule definition. Probability of C given P is the probability of C and P divided by probability of P. We'll split that up in the denominator because we don't know the probability of a positive test yet. So we'll write that as the probability of C and P plus C complement and P. We'll then use that rewriting of Bayes' rule that we had done previously and look what that results in. We can now find the probability of C given P using the opposite condition in terms of probabilities that are conditional on having the gene. So we've been able to flip our condition, which is really powerful. Now we have this in terms of probabilities that we have available. So we plug in our values. So in the numerator, we get 0.9 times 0.03. In the denominator, we get 0.9 times 0.03 plus 0.01 times 1 minus 0.03. So we get about a 74% chance. So if someone tests positive for the CF gene, there's still about a 74% chance that they are in fact carriers. We will end our discussion of conditional probability here. In the next video, we'll introduce a continuous probability situation by looking at the normal distribution. See you then.